Welcome, this is going to be our lecture video for January 6th. Let's go ahead and get started with a few more simplifying of single radical expressions. So go ahead, get those notes out, copy these two down. So how do I simplify the fifth root of 64 n to the sixth? So first thing is I'm going to focus on just the coefficient underneath my radical. I'm going to see if there's any integers to the power of 5 that can go into 64 evenly. So I'll just start raising different numbers to the power of 5. We'll start with 2 to the fifth. And when we do that in our calculator, we get 32. That one does fit in evenly. We should probably just do 3 to the fifth just to double check. 3 to the fifth is 243. So this was the one that we were after. Let's split that 64 into a 32 times 2. Alright, now let's deal with the variable. So a fifth root can only cancel out an n to the fifth, so I need to split that n to the sixth into an n to the fifth times n. Now there's still 6 n's there, but the fifth root can cancel out this 5 and an n can jump out of this radical. When I take the 32 out, it's going to become a 2 because 2 to the fifth equals 32, so fifth root n to the fifth cancel out. And when I take this n to the fifth out, it's going to become just an n. So now we've got 2n times the fifth root of everything left behind, which was just a 2n. So 2n, fifth root 2n. Alright, put a box around that. Let's go over to this one. Now we've got a seventh root. So let's raise different numbers to the power of 7 and see if we can get a number that goes into 768. So 2 to the 7th is 128. 3 to the 7th is 2,187. So let's see if 128 goes into 768 evenly. And it does, it goes in 6 times. So I could rewrite this, I'll bring it over here, as the seventh root of 6 times 128, except I like to write the 128 in front because that's what's going to come out of the radical, so 128 times 6. And then that x to the 9th, I want to split that into an x to the 7th times x squared. There's still 9 x's there, but I'll be able to negate this power of 7 and bring out just an x. And here I'm going to bring out a 2, because 2 to the 7th is 128. 7th root of 2 to the 7th would just be 2. So I'm bringing out an x and a 2, so we have 2x times the 7th root of everything left behind, which was a 6 and an x squared. And we'll put a box around this one. Alright. Goal for today is to refine our understanding of simplifying radicals and learn how to combine radicals with addition and subtraction. Why we're doing this is to be able to handle situations where we have to use multiple techniques to simplify a radical. We might need to put two radicals together and then simplify them. You're just going to be combining a lot of techniques. Alright. So here we have 4 different problems, all involving some addition and some subtraction. How are we going to simplify these further? So the trick is, if the index and the radicand match, then add the coefficients. So this is just like combining like terms. 4 root 11 plus 1 root 11, we can imagine there's an invisible 1 there, equals 5 root 11. The root 11 is just along for the ride. Just like how 4x plus x would equal 5x. 4 root 11 plus root 11 equals 5 root 11. Same thing happens here. The index is a 2, The radicands are both 13, so we can just do the 20 minus 10, and we get a 10 root 13. Alright, now in this next one, root 8 plus root 18, it doesn't look like these can be combined because they don't have the same radicand. Well, let's simplify both of them and see if then maybe we can combine them. So the 8 can be split into a 4 times 2, and this 18 can be split into a 9 times 2. I can jump out the 4 and the 9. Those will become a 2 and a 3 respectively. So I get 2 root 2 plus 3 root 2. Now the radicands do match, and I can add together these coefficients in front. So 2 plus 3 is this whole thing equals 5 root 2. So sometimes you need to simplify first to be able to combine. Alright, let's see if we can do something similar here. That 12, it does have a perfect square factor. That factor is a 4, so I should split that into 2 times the square root of 4 times 3 plus 48. I think I could, the biggest perfect square would be a 16. Yep, so I'm going to rewrite that as 16 times 3. Alright, now the 4 can jump out of this and become a 2. The 16 can jump out of this and become a 4. 2 times 2 over here becomes a 4, so we got 4 root 3 plus 4 root 3. Now that this part matches, we can add those coefficients so we can get 8 root 3. Alright. Now what about expressions where we're multiplying 3 things? Well, if we can get any 2 of them to match, we can combine those. If we can get all 3 of them to have a matching radicand, then we can combine all 3. Well, we start the same way by just taking out the largest perfect square factor. So for this one, that 27 could be split into a 9 times 3. That 12 could be split into a 4 times 3. I can already see that 3 is going to match up nicely. And this 75 can be split into a 25 times 3. Alright, now we remove the perfect squares, so the square root of 9 is a 3, the square root of 4 is a 2, the square root of 25 is a 5. So let's see what we have. Now we've got 9 root 3, I did the 3 times 3 to get a 9 there, minus 10 root 3, plus 5 root 3. Now you can add them all together, you can pair them off if you want. Here I'll pair them off, I get negative root 3 plus 5 root 3. Now we'll combine these. Negative 1 plus 5 is just a 4, so now we got 4 root 3. Final answer. Alright, what about something like this? 7 root 5 plus the square root of 3. This one here can't be combined further. We'll say it can't be simplified further. So the key is getting that radicand to match. Here we're not going to be able to get that radicand to match, so we don't want to try and force the issue. These 2 radicals do just have to stay separate. So it's going to happen from time to time. Alright, trying a few more. We got 4 root x plus 3 root x minus 5 root x. Here, index, radicand match, we can just combine those coefficients. So 7 root x minus 5 root x. Pair these off now, we get 2 root x. Alright, here we've got a variable underneath the square root that could be simplified. That x cubed could be split into an x squared times x. So we've got 3 square root of x squared times x plus x root x plus the square root of 3. That x squared jumps out as an x, and now I've got 3x root x plus x root x plus the square root of 3. Now that the index and the radicands match here, we're going to add those coefficients. We're going to do the 3x plus an x, and that's going to become a total of 4x. And then keep that root x, and then the square root of 3. That was just along for the ride the whole time. We were never able to add it in. All right. So what if the index is different but the radicand is the same? There is a way to still combine these, and it's to use a special property of radicals. We haven't talked about it yet, except for with one of my classes, but it is the fact that the square root of 2 could be rewritten as 2 to the 1/2. These are equivalent. Similarly, the cubed root of 2 could be rewritten as 2 to the 1/3. Those are equivalent. This is a useful way to plug in radicals into a calculator if you don't know how to get to the right spot to change the index of your radical. You can just treat them as exponents and then plug in the exponent, which is often easier to find. So once I rewrite these radicals with exponents, 2 to the 1/2 times 2 to the 1/3, I might remember a rule about multiplying exponents, which says if you multiply exponents with the same base, you can add the exponents. So this here is going to become 2 to the 1/2 plus 1/3. And let's just kind of do this in our heads. 1/2 is the same as 3/6. 1/3 is the same as 2/6. So 3/6 plus 2/6 equals 5/6. So this is the same as 2 to the 5/6. All right, now I want to do a few things to turn this back into a radical. So I'm going to split apart that 5/6 to make this 2 to the 1/6 to the 5. So pulling the 5 off the top and writing it as a separate exponent. And now 2 to the 1/6 becomes a 6th root of 2, all to the 5th. And I can write that to the 5th inside or outside the radical. If I bring it inside, then 2 to the 5th can become a 32, and I've got the 6th root of 32. That's my final simplification. All right. Consider this just a preview. We'll do a lot more stuff with the exponential form of radicals later, but here is a way to simplify this. All right, another one. So negative 2 root 3 minus 2 root 3. Right off the bat, I can combine those to be a negative 4 root 3. The square root of 12, that 12 could be split into a 4 times 3, and then the 4 could be brought out as a 2. 2 times 4 is an 8, so we've got plus 8 root 3. So negative 4 root 3 plus 8 root 3 is going to just be 4 root 3. We can simplify this whole expression here down to just 4 root 3. All right, I believe this is our last one. Square root of 10 times the square root of 8. So 8 does have a perfect square factor, but we don't want to necessarily simplify that out first. Instead, we want to put this together, make this the square root of 80, and then from this point, look for the largest perfect square factor of 80. So if I write out my perfect squares, 4, 9, 16, 25, I get that actually 16 is the largest perfect square factor. I can now that I've put these two numbers together to get an 80, I'm going to split it apart, but this time I'm going to split it into a 16 times 5, and then the 16 can jump out as a 4, and this can become a 4 root 5. So square root of 10 times the square root of 8 becomes 4 root 5. All right, I'll embed a few more for you to practice here. We'll call that good for this lecture video. Have a good rest of your day.